out of them. I know I should make stew out of them. I know I should. I just can't do it. It's like killing your grandma. Frog number 3. A little feathery grandmother.
Grandma? By the time you guys realize it's what bird it is. Have someone else take the feathers off and have them, you won't even know what bird it is. It's just
You're scaring the piss out of me right now, Riley. Your efficiency, your brutal efficiency. It's amazing. I appreciate that. I'm not gonna kill my birds.
Just like when you cut up your cow, you're not gonna know it's your cow.
But I don't have a cow.
I know.
Why not?
I'm a recovering vegetarian, for God's sake. 3 birds. Now, you guys already know what the average number of girls is going to be. What's the average number of girls going to be? Before we even start, what's the average number of girls going to be? You know what it's going to be.
2.7.
It's going to be 2.7. Because we added 1 more bird. And every bird we... Now, Haley, we'll come back to the calculation. I promise you that. But we added 1 more bird. Every bird is 0.9 girl, 0.1 boy. So you added 0.9 more to the 1.8, which makes 2.7.
Okay,
now, if you don't like that, and it's okay to not like that, we'll do the calculation momentarily. But for right now, just realize every time you add a bird to your flock, you're adding 0.9 more girls into your flock. You're also adding 0.1 more rooster potentially, on average, but you're adding 0.9 more girls on average into your flock. So the average number of girls is going to be 2.7 per 3 birds. Now, if you don't like that, if you want a calculation, we'll do the calculation momentarily. But in order to do the calculation, we have to have the distribution to actually calculate it. Because these damn things are not at 100% yet. Not yet. We're getting there. Okay? So, number of girls. And the chance of that number of girls. Okay, what are the possibilities here? 0. 1. 2. 3. And that's it, right? Because I bought 3. So I might have all roosters, I may have all chickens, I may have a girl and 2 boys, or a boy and 2 girls. Those are my options, right? Those are my options. Now, how likely are those options? Pick one and give me the probability associated with it. Your choice. Your choice which one you want to use.
0.
0! Random. What's the chance? I bring home this, and they're all boys.
Oh, 0.0001.
Good. So what Randall just did was he reduced it to a simpler problem. What's the chance the first one's a boy? Well, it's clearly 10%. What's the chance the next one's a boy? Still 10%. What's the chance the last one's a boy? Marge, Bertha, and Mary, all boys. 1 in 1,000. You should not have a box with 3 pullets in it that are all boys. It should only happen 1 in 1,000 times. Now that might be the time you go in to buy 3 birds. That could happen, right? It could happen and you'd call it a what?
Outlier.
As it very much is an outlier, but it could happen. The definition of an outlier is not something that never happens. It's something that rarely happens. Not as it should not happen usually, but it does happen. Today in class, just to drive home in 105, the definition of what 50% probability meant, and I couldn't use my computer because the computer blew up in the classroom. I fired up Excel, and I generated 200 random 1s and 2s. I said, pretend that 1 is heads and 2 is tails. And I pressed enter, and there was a string of 14 1s in the very beginning. Knocking down the point that you can get that happen in a random string of occurrences. There is a place and time somewhere where a whole bunch of people go in and buy a whole bunch of pullets and they all come out with roosters. It's the infinite monkeys theorem. Have you ever heard that, the infinite monkeys theorem? You ever heard of this? Some of you have. Take an infinite number of monkeys, put them in an infinitely large room, give them each a typewriter, and let them pound away at the typewriter. Eventually, at some point, one of them will type, I think, comma, therefore I am. At some point, one of them will type the entire works of William Shakespeare. At one point, one of them will type the entire Bible, word for word, without missing a note. That's how big infinity is. They will randomly create those strings of text. You would never expect that from monkey slandering a typewriter, right? You've heard the phrase, even a blind squirrel gets a nut from time to time? It's exactly the same thing. Randomness does allow for these clumps that appear to be meaningful occurrences. So I'm not saying that you can't have a time where 10 people go into a store and each buy 10 chickens and they all come out roosters. But the first thing I would think if that happened was, are you sure you're getting 90% chickens out of this flock? It can happen. It just shouldn't happen. Yeah, Faith.
So that's for that. It can happen that you shuffle a deck of cards and then the next shuffle is the exact same order.
It can happen. It's just so incredibly unlikely that it will happen. Thank you. Yes, exactly. It's all tied together. And what this is, whenever you do these calculations, it's an average. On average, 1 in 1,000 trials. So imagine Max walking into that store 1,000 times. Or imagine Max over 1,000 years, little Yoda Max, over 1,000 years, walking in once a year, buying 3 girls or 3 birds and going home. According to this, in one of those 1,000 years, he should walk out with 3 roosters. According to this. That's an average. That's an average. He might never do it. It might happen 2 years in a row. It might happen 2 years over those 1,000. But it averages to 1 in 1,000. Fair? Okay. Let's attack another one. Which one do we get next?
1.
3? Why 3? I love it. 3. Why'd you guys go with 3?
Because it's easier.
It's the easiest one to calculate next, right? What's the chance they're all girls?
0.729.
So that's the chance that Bertha comes out being a girl. Here's the chance that Nancy is a girl. And here's the chance that Marge is a girl. What does it work out to be?
72.9%.
Once again, it goes down from last time. It's dropped again. It's getting harder to get all girls. It's getting harder to get all girls. 73% of the time, roughly, you're going to get all girls. So if I send Max into that store over time, over 1,000 years, in 729 of those 1,000 years, he's going to come out with all girls. In one of those 1,000, he's going to come out with all boys. What's the relative frequency of the mixes and matches in here? Faith, help me!
The one girl and 2 boys is 0.027.
Tell me how you got that.
I did the 0.1 times 0.9 times 0.9 plus.
Stop right there, my friend. Why aren't you just done there?
Because that's just one order that can happen. So now I have to switch it to where I made it 0.9, 0.1, 0.9.
So this is like snake eyes, and this is like boxcars, and this is like when the dice can be different numbers. You have to allow for those different numbers to be on different dice. Every one of these chickens is a die that you're rolling. Every single one of these birds is a die that you're rolling to see what it comes out, whether it's a boy or a girl. If you're saying one of them's a girl, the next question you have to ask is, which one is a girl? Is it that Bertha's a girl, and Marge is a boy, and Nancy's a boy? Because that's what Faith just had me write down on the board. But is that all the possibilities? No, it could be that Bertha's a boy, Marge is a girl, and Nancy's a boy. Or there's 3 possibilities for that assignation, isn't there? Because either Bertha's the boy, Marge is the boy, or Nancy's the boy, and the other 2 are the girls. Randall, go!
Wouldn't that be 0.9, 0.1, and 0.1?
Yes,
That's what I found, yeah.
Oh, you say it wrong?
Yeah, I said that wrong.
That's what I found.
0.1.
Oh, you did! It should be 2 0.1s and a 0.9. Yes.
Yeah.
2 boys and a girl. Sorry, yes. That's 0.1, 0.1, and 0.9. I trust you guys. It's all good. We fix it. So, what Faith just said was 0.1 times 0.1 times 0.9 plus, now she lets the 0.9 move around. 0.1 times 0.9 times 0.1 plus point. Is it okay? Is it okay if we just simply do this?
Okay.
If I put a 3 out front, it's called the binomial coefficient. It means there are 3 ways to do it, and it makes life much easier for us. We could have also done it over there, but that didn't seem quite as bad, did it? That one was like, oh, it's just 2. We just add this and then flip it around. As the flocks start getting bigger, it starts getting more and more ridiculous to be writing those out all the time. Go ahead, Scott.
Oh, wait. I don't know. I'm trying to think, because, I mean, that's not the only combination there could be.
No, we're doing this one right here.
Okay.
We haven't gotten to this one yet. Let's finish this one off, though. So this is 0.009 times 3. Do I do this right? 27?
Mm-hmm.
Yeah.
2.7.
So 2.7% of the time, Max should go in and come out with 1 girl and 2 boys. 1 girl and 2. So out of 1,000 trials, in 27 of those trials, we got 2 roosters and a hen in our box.
Because X equals enough.
Yes, because X is the number of girls. Exactly. Is that okay? This is why I love you break these flocks down one bird at a time. One bird at a time. Okay. Now, we know we can figure out what this probability has to be from what we have already. Because we know we can add that and that and that and subtract from 100%. We're done. Let's try to calculate it directly though. Just to practice that, right? Just to practice that idea that you guys are already picking up. So if I want 2 girls, that means I gotta have 1 boy and 2 of the girls, right? That's a 0.9, 0.9, 0.1. And why 3, Sandy? Thank you. Because once again, there are 3 ways to assign either, and this is good, there's 3 ways to assign either the rooster or the 2 girls. Right? You have to pick which one is now the lucky rooster. Is it Bertha, or Marge, or Nancy? You have to figure out where that assignation is. Where does that come to be? Let's see, 0.81, 0.081, 243? Did I do that right? And does it check, more importantly? Does it check here? Oh, it does, look at that. It sums to 1. Yay. Now, what I love about this is, all of a sudden, that's pretty high, isn't it? That's 24.3% of the time. That's roughly a quarter of the time. That means if I send Max in 4 years in a row and say buy 3 birds each time, that's telling me that I should expect in one of those 4, 25% of the time, to get a rooster mixed in with the girls. You see, it's getting harder to avoid the roosters. It's getting harder to avoid the roosters. It was pretty easy before. But now that we're buying more and more girls, the chance of that 1 or more roosters popping up is starting to increase. Because you got to realize, the last line of any of these distributions is the only one without roosters. Everything else has at least 1 rooster in it. And this is shrinking away, which means everything else is increasing, which means I'm getting more and more likely to get the roosters picked in. You see what I'm getting at here, friends? This was my concern at the desk of High Desert Ranch at home when I picked the 4 off the desk. It's a 1 in 3 chance. We still haven't seen our 1 in 3 yet because we haven't done 4 chickens yet. Ask me that question, Corey. Ask me that question.
Well, I was just going to wait for a good time to ask how to find the expectation.
Good! Yes, sir. Thank you. That's a perfect segue. It goes back to what Haley asked. How the hell did you know that was 2.7? The expectation is still just the average. The average is the expectation. How many girls would you expect in a box of 3 birds? How many girls would you expect? So we know the answer is 2.7, but how would you get that without... The only reason we know that is because we did 1 and 2 birds before this. So how would you get that from this? And this goes all the way back to week 3. It's a weighted average again. You take each probability times its data point. So you go 0.001 times 0 birds, or 0 girls, to plus 0.027 times 1 girl, or 1 bird, 1 girl I guess, plus 0.243 times 2 girls, plus 0.729 times 3 girls. That's your average. 72.9% of the time, you get 3. 24.3% of the time, you get 2. 2.7% of the time, you get 1, and 1 in 1,000, you never get any. That's your average. It's the same average calculation you guys use for Chuckala. How much money are you winning on average? It's the same calculation. Different probabilities, different context, but the exact same calculation. What does it come out to be? No coincidence. 2.7. Let's do it together. Let's do it together. Make sure you can see it.